Hello students, it's Dr. Sansom. Today we're going to be talking about sigma and pi bonding in C2H2 using valence bond theory. So the first thing we should do is draw a Lewis structure. So we'll have carbon, this molecule is linear, and we'll have 2, 4, 6, 8, 10 electrons total. 8 from the carbon and 2 from the hydrogen. My carbons here don't have an octet yet, and since I can't make a double bond with hydrogen, I'll move these electrons into the middle, make a double bond, and move these other electrons into the middle, and make a triple bond. So this is going to be my Lewis structure for acetylene. So each of these carbon atoms has 2 electron groups, which means that I'm going to have sp hybridization, and it also means that I'll have 2 extra p orbitals on each atom. So in this first diagram, we see the sp orbitals overlapping between the carbon atoms to make the bond, and the sp orbital overlapping with the s orbital between carbon and hydrogen to make the other sigma bonds. So those are the 3 sigma bonds in the molecule. We'll also see some p orbitals that are oriented going up and down. And then we have some p orbitals that are oriented, I'll make them blue just for clarity, that are oriented sticking out of the page and going back into the page. Okay? So the black ones that I've drawn going up and down are the ones that are going to make the bond that is above and below. So this part here and this part here, those are formed by the black ones that I drew, the ones that were sticking up and down, and it makes the pi bond that goes above and below the axis. And the ones that are sticking forward and backwards are going to make this pi bond that's in the back and the front of the page. So that's the second pi bond. So if we're describing the bonding here, we'd say an sp hybrid orbital on each carbon forms a sigma bond with the s orbital on hydrogen. Those are the ones on the outside. Second, we have 2 sp hybrid orbitals forming a sigma bond in between the carbons. That's our third sigma bond. And then we have the black pi bond that's going up. And we have the blue pi bond that's coming out of the page. So 2 of those are our 2 pi bonds in the molecule. Now, whenever we have single bonds, they're always sigma bonds, and that's because sigma overlap is going to be greater than pi overlap. It makes it more stable. It lowers the energy more, it makes a stronger bond. If we're talking about a multiple bond, then only one of the bonds is a sigma bond and the others are pi bonds. So for example, if we have a hydrogen-hydrogen single bond, we know that that one is sigma. If we have this double bond between carbon, there's 1 sigma bond plus 1 pi bond. In a triple bond, we have 1 sigma bond and 2 pi bonds. The rules for pi bonding are like this. We have to hybridize enough orbitals to make sigma bonds and handle lone pairs. Okay, so if I look at my atom, I count up how many bonds there are, just any kind of bond, and then how many lone pairs there are, and add those together, and that's how I decide what the hybridization is. And then if we have any left over p orbitals, they can be overlapped to make pi bonds. So if I have a triple bond, that's going to be a single sigma bond and 2 pi bonds. Now we have in benzene 12 sigma bonds. There's the 6 sigma bonds that are between all of the carbon atoms that are shown in the diagram. And then there's also 6 sigma bonds to hydrogen. They're not shown in the diagram, but they exist. So that's our 12 sigma bonds. And each of these carbon atoms is going to have a p orbital. it's shown here, this red and blue, right, is going to have a p orbital that's sticking up from the plane of the molecule. And those orbitals are what can make the pi bonds. But just like a Lewis structure isn't a perfect example or like a perfect representation of a molecule with resonance, we're going to run into the same problem with valence bond theory. We don't have, a double bond here and no double bond there, and then a double bond here and no double bond and then a double bond here, right? That's not how it works. Instead, all of these orbitals are going to be delocalized, and they make what looks sort of like a donut on top of and on and below the plane of the molecule. And because all of the p orbitals can overlap in this way and they make this big giant cloud, that makes the molecule really stable. So conjugation is like another word for alternating single and double bonds. And it's the same phenomenon that results in aromaticity. In order to organize these terms, I'm going to just start putting things together. So I'm going to take SP, SP2, SP3, SP3D, and SP3D2, and I'm going to put them together with hybrid, because those are all hybrid orbitals. I'm going to take S, P, and D, and I'm going to make those unhybridized. I had to make up that label, so I did. I'm going to put bonding together with sigma and pi and orbital overlap. And then I'm going to put linear, trigonal, planar, tetrahedral together with molecular geometry. So I think the only word that I haven't used here is conjugation, and I'm going to put it together with this other one that's related to bonding, because it's a special type of bonding where we have those alternating single and double bonds. Okay, that's everything for today. Thanks.